All right, here's your joke of the day. What do you call a parade of rabbits hopping backwards? A receding hairline. All right, today we are talking about nonlinear inequalities, which we have seen a few of these before in our first unit, actually. There are a few on our review and a few in the homework, but we had a calculator because if they're nonlinear inequalities, then really we either need to have a calculator or know how to graph what we're looking at that's nonlinear, which at this point we know how to graph polynomials and now rationals. So we're going to look at those two nonlinear inequalities. Before we get there, though, I want to look at a linear inequality so that we can see why this works, what we're about to do. So if we have a linear inequality, that just means we have just an x to the first in the inequality. Like this 2x plus 4 is greater than 0. And then of course we can solve it like an equation and we end up with x is greater than a negative 2. However, we can look at this graphically that our 2x plus 4, if we treated that as the function, so basically that's our y or our f of x, and we graphed it, so our 2x plus 4 would have our y-intercept at 4, and then our slope of 2, so I'm going to go down 2 into the left one, down 2 into the left one, it would look like this. And notice, if I am looking for where my y's are greater than 0, so my 2x plus 4 is greater than 0, that means that I'm looking where my y's are above the x-axis. So here's where they are greater than 0. And my answer is going to give the x values where that is true. So my x is going to be every x value that is greater than negative 2. So this is the answer to when is this function greater than 0, when it is above the x-axis. And the answer is when the x's are greater than negative 2. So for a linear inequality, it wasn't necessary that we graphed it, but this is the same logic that we're going to be using to solve our nonlinear inequalities. Because when I have something like this x squared minus 9, I've got a little scribble cloud up here, this x squared minus 9 is greater than 0. If we try to solve something like this, what typically happens with students is that they go ahead and try to solve it like a linear inequality, and then they get to this point where they take the square root of both sides, and they don't know what to do with this. This is not really helpful. X can't be greater than, well, it can be, but it doesn't make a whole lot of sense for it to be greater than 3 and greater than negative 3. That just means it's greater than negative 3, which is not true for this inequality. It doesn't make sense, and we're not going to solve it this way because that's confusing. What we are going to do is look at the graph of f of x, which would be shifted down 9, and then we'd be looking at a parabola. Now this positive and negative 3 are important. They're x-intercepts, so this is a negative 3 and this is a positive 3. But by graphing our function, we can tell our function will be greater than 0, which again, we're talking about the y value, the f of x, being above the x-axis, so greater than 0. Over here, it's greater than 0, and then over here, it's greater than 0. So if I'm giving the x values, it does have to do with my negative 3 and positive 3, but by looking at it, I can see my x values where my y is greater than 0 is from negative infinity to a negative 3. But then now I'm below the x-axis, now I'm less than 0, and then from 3 to infinity. So anytime we have an inequality that is nonlinear, we're going to have a different approach. Where if I had a calculator, something like this, I don't know what I'd use a calculator for, but if it's something more complicated, if I have a calculator, I would graph it, and I'm looking for where it's either above or below the x-axis, depending on what your inequality is. Or if I don't have a calculator, then I'm relying on the fact that I can factor it and look at what that graph looks like in order to figure out where it's above or below. Okay, so the first thing that we need to know before we get into our nonlinear inequalities, something called critical values. So critical values are just x values where the graph could change from either being below to above or above to below the x-axis. So x values where the graph could change from positive to negative or negative to positive, meaning values where it could go from being above to below or below to above. Because remember, we're going to be looking for where it's either greater than 0 or less than 0, sometimes equal to as well. But this is telling me these are the places where it could change, so I could just look at those places, and then in between them it would have to be just above or just below, because those are the only places where it can change. So for polynomials, it's pretty basic. Polynomials are continuous functions, so the only critical values that polynomials have are at x-intercepts. The only way that a polynomial is going to go from being below the x-axis to above or above to below is if it crosses through that x-axis. We've seen that with the intermediate value theorem, that if we have a y value above and a y value below, then we know there has to be an x-intercept in there because polynomials are continuous, so it's got to cross. Okay, so if we are trying to solve an inequality that involves a polynomial, it's not linear, it's got something, a higher power than just 1. The first thing that I want to do, and this is true for rationals as well, is get everything on one side to where I am comparing to 0. So I can deal with looking at my graph and knowing whether I'm above or below the x-axis. So my first step here is just subtracting that 16 over so that I can compare to 0. And now I could even note off to the side that if I'm looking for this function to be less than 0, then really I'm looking for where is it below the x-axis. And I think that helps us to remind us that this is what I'm looking for in the end. This is the type of question that sometimes students work part of it and then they forget what they're actually trying to answer. In the end, I should be giving the interval for x's where my y values or my f of x is below the x-axis. I'm not done until I've said that. Okay, so now that I'm at this point, because the only critical values that I have for polynomials are x-intercepts, now I'm going to go ahead and find the x-intercepts. So we'll just say we've got critical values here, which are x-intercepts. So at this point, we are going to ditch the inequality because I'm actually finding the x-intercepts. If I keep it as an inequality, it is confusing. We're setting it equal to 0, factoring, 0 multiplied to be -7, had to be -6, looks good. So we should get x-intercepts at 7 and -1. Those are the critical values. These are the only places where it could cross the x-axis. Okay, so now I am going to analyze my function. I do not need a very specific graph. In fact, I'm not even going to include a y-axis because it doesn't matter. I'm looking for where it is below the x-axis. So I'm going to keep this as a number line where we are looking for where it's above or below. It doesn't matter how far apart these numbers are. I'm just using these values as these are the only places where it can change. And then I'll use my polynomial rules. This is a quadratic. It's facing up. It's smiling. So I'll go ahead and sketch that in where we can tell where it crosses the x-axis. We can see that our function will be above the x-axis to the left of -1, and then it's below the x-axis in between, and then it's above the x-axis to the right of 7. So in the end, my function is below the x-axis, or x squared minus 6 minus 7 is less than 0 over the interval, or when x is on the interval from -1 to 7. And you don't have to write that sentence every time. We can just use the interval -1 to 7, but I just want to be clear that that's what we're answering. We're saying this is true, this inequality is true when x is on the interval from -1 to 7. Of course, if it was less than or equal to 0, then we would include -1 and 7 in our interval, but this was strictly less than 0, so it's just from -1 to 7. Okay, so we could have a polynomial that is a little more complicated. For what we are dealing with, we will deal with almost all factorable polynomials. So if this was something that wasn't factorable, goodness, you would have a calculator to where you could find some x-intercepts that way and see where it's above or below the x-axis. I don't know, or maybe we're working it together in class. But for what I'm expecting from us, we're going to have factorable things that we can find x-intercepts easily and look at the graph. Okay, so for this function, we already have it compared to 0. Remember, that's the first step if that's not true. Because it's true, I don't need that first step. So now I'm going to go about finding my critical values. Remember, that means that I'm looking for my x-intercepts. It's the only place where it can cross the x-axis. Go ahead and set it equal to 0. So for this, let's try factoring by grouping. We would hope that it's factorable by grouping, because otherwise we need to take a much longer route. So factoring an x squared out of the first two terms, and a -4 out of the second two. Good. Turns out that it is factorable by grouping. What we got in parentheses is the same both times, so we're good there. So now we can factor out our x plus 2, and then we're left with an x squared minus 4, which equals 0. From here, we could keep factoring with our x squared minus 4. It is a difference of squares. Or since you're finding your x-intercepts, we could set that x squared minus 4 equal to 0 right now. But continuing to factor is helpful because we are eventually going to graph it. So this lets us know I do have two x plus 2's, and that will be important for how we graph our function. But my x-intercepts will be at a -2 and +2. So those are my critical values, the only place where it can cross. Now before I graph, it might be a good idea to go ahead and write my whole function in simplified factored form. To go ahead and say x plus 2 squared, there's a lot of 2's in here, x minus 2. And now we are ready to sketch a graph. Again, I don't need a y-axis, I need my two critical values. And then my graphing is going to be a little bit more complicated here because it's not a parabola. I can go to my original to see that that leading term is positive and it's odd, so my end behavior will be like a positive sloped line. So it'll go from negative to positive. I can also see that my x plus 2 is squared, so that means that my x-intercept of -2 will bounce. And then my x minus 2 is to the first, so my x-intercept at 2 will cross. So now we've got starting below, we're bouncing, and then crossing. Okay, so always going back to what we're answering. This time I didn't write it at the beginning, but it definitely helps that at the beginning I could have said, okay, if I'm looking for where this function is less than or equal to 0, we're saying below or equal to the x-axis. So where our y values are less than or equal to 0. So looking at my graph here, I've got below the x-axis, and we're equal to it, below the x-axis, and then equal to it, and then to the right of 2 we're above the x-axis. So if I'm giving the intervals where we are less than or equal to 0, that means that I'm less than 0 at negative infinity. That is the least x, where I'm less than 0. And then I can include negative 2 because it was or equal to, and then I can go all the way until 2 and include it because it is equal to 0 there. So these are the x values where my y's are less than or equal to 0. Again, I'm including my negative 2 and 2 because it said or equal to. If the question was strictly less than, then I would give the interval from negative infinity to negative 2 and not include it, so I'd have a parenthesis, and then union with negative 2 not included to 2 not included. So I would give those two intervals but not include the negative 2 and the 2 because that's where it is equal to 0. Okay, so now rationals. Rationals are slightly more challenging, just because rationals are a little bit more challenging to graph. So rationals are still going to have critical values at x-intercepts. Because I could still have it change from being above to below or below to above the x-axis at an x-intercept, but also rationals are not always continuous. Actually, usually they're not continuous. By nature, they're not continuous because they have a denominator. So not only could it cross at an x-intercept, but it could also cross at vertical asymptotes. Okay, so I'm going to show you what I mean here. I'll get a vertical asymptote here, maybe a horizontal asymptote here. Okay, so let's say I've got this function where I'm going to be above over here. Okay, so let's look at where this function is above and below the x-axis. So starting from the left, I'm above the x-axis here, but then at an x-intercept I cross, so that's like the polynomial. I can cross at an x-intercept to go from above to now I'm below. But now, at this vertical asymptote, I all of a sudden flip from I was below and headed to negative infinity, and all of a sudden on the x value directly to the right of my vertical asymptote, now I'm above. And then I'm going to stay above here. Okay, so we have the case where I switch from above to below at an x-intercept, but I could also change from below to above or vice versa at a vertical asymptote. So we see both things happening. We have to analyze the intervals in between those things. So once I find my critical values, so I had the x-intercept and the vertical asymptote, I would need to know what's happening to the left of that x-intercept, what's happening in between the x-intercept and vertical asymptote, and then what's happening to the right of the vertical asymptote. So I'm going to end up with any interval in between, very similar to figuring out the intervals between the critical values here, but this was a little bit more straightforward. We knew that they were all x-intercepts where we could have vertical asymptotes come into play here. Okay, so we're going to start with one that's not super complicated to begin with. My first step is still going to be the same. I still want to compare it to 0 so that I can look for above or below the x-axis. So for this one, I'll subtract 4 from both sides to start with. But I do have to have this as one rational, or it's easiest to have this as one rational function before, one fraction, before I look at x-intercepts and vertical asymptotes. So this is why we looked at, one of the reasons that we looked at rational operations, is that if I'm combining these, I do need a common denominator. So I'm multiplying that 4 by x over x. So my 1 over x minus 4x over x, which is 1 minus 4x over x. And when you get decent with getting common denominators and combining rationals like this, you can go straight from that first step to the last one where we know the denominator will be x, and you've got a 1 minus 4x in the top. Okay, so now our critical values. Remember, we've got x-intercepts to look for, and then we also have vertical asymptotes. So first with the x-intercepts, I've got 1 minus 4x over x that I'm setting equal to 0. Now the nice part about finding x-intercepts of rationals is that that denominator does not end up affecting x-intercepts, because if I multiplied both sides by x, I would get an x times 0 on this side. So it really is just the numerator that is going to give me an x-intercept. Or if you think about cross-multiplying, you would get your x times 0 and then 1 minus 4x times 1. So 0 would still equal that. Okay, so once we subtract 1 from both sides and divide by a negative 4, we will get a positive 1/4 as our x-intercept. And then for vertical asymptotes, and sometimes we have 1, sometimes we have more than 1. Remember, our vertical asymptotes come from excluded values where we know x can't be 0 in this situation, the denominator can't be 0. And then if it cancels, if this could factor and cancel out the x, it would actually be a whole. But since it does not, that excluded value is a vertical asymptote. So we've got 1/4 and 0 are our critical values. So now I am looking at 0 and 1/4 on a graph. Here's where it's quite a bit different than a polynomial, because a polynomial I could look at end behavior and my bounce wiggle cross and graph it real fast, and then I know exactly what it looks like. For rationals, it's not as clear. Remember, when we graph rationals, a lot of times we have to plug in values to the left and the right of vertical asymptotes to know even what's happening. So that's exactly what we're going to do. If it only crosses the x-axis at 0 and 1/4, that means everything to the left of 0 has to be doing the same thing. It's either positive or negative. Everything in between is positive or negative, and everything to the right of 1/4 is positive or negative. So I'm going to plug in one value to the left of 0, and that will let me know what they're all doing to the left of 0. So for instance, I would plug in -1, and I don't really care what the value is, I just care whether it's negative or positive. So if I plug in -1, I would get 1 plus 4, so positive, over -1, which is negative, so positive over negative is negative. I just care that it's below the x-axis. I would plug in something in between 0 and 1/4, so this kind of stinks because it's going to have to be a fraction. But with my numbers that I've got, 1/8 isn't too bad to plug in. So be smart about what you're choosing in your interval. If you could plug in 0, I always plug in 0. But if we plug in 1/8, that would just be a 4 over 8. So 1 minus 1/2, which is positive, over 1/8, which is positive. So positive over positive is positive. To the right of 1/4, we could plug in 1. So our 1 minus 4 would be negative, over a positive is negative. And a lot of times it does alternate like this, where it goes negative, positive, negative, but we don't want to rely on that. So try something in every interval. We do have cases where over a vertical asymptote, it doesn't change from above to below or vice versa. And we do have cases where we just bounce at an x-intercept and not actually cross. So go ahead and plug in each interval. If you do get two signs back to back, you might double check it because it doesn't happen a ton, but it does happen. Okay, so we're testing in each interval. Now, finally, we are looking at where our function, well, really right here, where our function is less than 0. So I'm looking for where it's below the x-axis, and that is happening from -infinity to 0, and then from 1/4 to infinity. All right, one more example. And if you hear that sound in the background, that is my dog eating. One more example. This one's a little bit more challenging in the simplifying department. So first things first, we're getting everything on one side. It really doesn't matter which side you move it to. So we could move 4 over x plus 5 or 1 over 2x plus 3. We'll just keep going the way that we've been going. So I'm going to move everything to the left. And then we do want one rational out of this so that we can see our x-intercepts and vertical asymptotes. So from here, I need a common denominator. They don't have anything in common because I can't factor anything out. And sorry, I'm going to pause this for a second. He's being loud. Okay, so what I was saying, we can't factor anything out of either of those, so we know that they don't have anything in common. And so that means I have to multiply the first fraction by this 2x plus 3 over 2x plus 3, and the second fraction by an x plus 5 over x plus 5. So their common denominator will be a 2x plus 3, x plus 5. And I wouldn't multiply these together because in the end we're going to be looking for our critical values anyway, so these will give us our vertical asymptotes. So I'd leave it in factored form. In the numerator, we've got this 4 times 2x plus 3, so an 8x plus 12. Make sure that you distribute. Over here I've got a -1, so either make sure you have a negative and put it in parentheses, or go ahead and distribute the negative. So -1 times x, a negative x, and a -5. Distributing both of those. So last step here in simplifying, combining our like terms in the numerator. And now finally I can go ahead and look at my x-intercepts, or my critical values that are going to be happening at x-intercepts. Remember, every time that I set a whole rational function equal to 0, that when I cross multiply my denominator goes away. So I could go ahead and set just my numerator equal to 0. And I'm running out of room here, so that's what I'm going to do. So I will end up with an x-intercept at a -7 over 7, so a -1. And then for vertical asymptotes, we can look in our denominator and see our excluded values would be at a -3/2 and a -5. Neither of those factors will cancel, so I know they're not wholes, they are vertical asymptotes. Okay, so we've got on our number line at -3/2, so that is going to be our least. -3/2 is -1.5, so, oh, that's not my least. I got a -5. What am I doing? I'm just going to start over. Ignore the first one. Got -5, -3/2, and -1. Again, it doesn't matter how much they're spaced out, so I'm not worried that, you know, -1, -3/2 are closer together than -3/2 and -5. That's okay. So now we are testing our intervals, and we've got 4 different intervals to test. So I'm going to pause this for a second. You might go ahead and tag team it with your group, where you've got somebody plugging in something to the left of -5, something plugging in something in between each interval. Try this without a calculator, but remember, you are just trying to see if it is positive or negative. We do not care what the actual value is. So pause the video, go ahead and test values. If you're just working on your own, at least try a few of them. See if you agree with me. Pause the video for a minute. So we should get that to the left of -5 is negative. And then we've got positive, negative, positive. So again, a lot of times it alternates like this. If you didn't get one of these correct, you might try again or use a calculator this time to plug in a -6. I would plug it in here. Maybe plug in a -2, a 0 for that part. Oh, sorry, not 0 there. This one's kind of tricky. Plugging in maybe a -1.2. I don't know. That one might be one that you need a calculator for, unless you can come up with a fraction that works. I guess something with a 7 might help. A -8/7 might be easy to do. Okay, and then something 0 would be good right there. Okay, so once we've got our negatives and positives, we are answering where our function is greater than 0 this time. So we should end up with where we are positive from -5 to -3/2, and then again from -1 to infinity. So these rational inequalities, I would take really slowly, there are a lot of steps to it, and if we don't simplify correctly, now you've got the wrong x-intercepts and the wrong vertical asymptotes. So go through this part slowly where you're getting everything to be one fraction, getting a common denominator. Be careful with your numerator that you're distributing things correctly, finding your x-intercepts, vertical asymptotes, and then testing. But just a reminder that when we were dealing with our linear inequalities, we were just looking for critical values at x-intercepts. So we just had to find x-intercepts and then use in behavior and bounce book across to graph it and see where it's above and below.